Alright, welcome to Unit 2.22. We're going to continue looking at polynomial identities that we've looked at already. We're going to work on those, and then we're going to get into what's called the Binomial Theorem, which is kind of the culmination of polynomial identities. It's incredibly helpful. It's actually used in proving one of the most well-known facts about calculus, and it's just in general helpful, whether it's statistics or probability. It shows up all the time, and so it's important to start thinking about now. So let's go ahead and get started. Alright, so you'll remember this one. We took a look at this the other day, and it seems like it's a lot of work, but what we did was we thought, okay, to prove that this x to the n minus a to the n is the same as this whole thing over here, what we're really trying to do is what? Well, we're trying to make the right side, simplify the right side to make it look like the left. Okay? And to get a handle of how we can actually do this, a technique that we talked about is picking an n. Okay, so maybe pick n equals 4. We did it with n equals 3. And see if you can, how you would simplify the method by which you would end up showing that the right side is equivalent to the left side. And then take that exact same strategy and just apply it to the general case up here. Okay, so go back and look at your notes. Go ahead and try this simplification and think very clearly about how you're going to actually the method by which each thing is going to cancel, and then apply that to the big case up here. So it's a lot of work. I want you to try this all on your own. You can absolutely do it. If you get stuck, that's okay. Just kind of rewind a little bit and try from where you last had something that made sense. And then I'll spend about a minute or two talking about it, but we're going to move on after that. Alright, so we want to try and clearly understand the pattern that goes on that hopefully you saw in doing this example up here, and we're going to then apply it to the general case. So if I look at the first term in my binomial, which we'll get used to in a second, stands for something that has two terms in it, bi meaning two. So if I look at the first term in my binomial, I'm going to multiply it by every term on the right here. And when I multiply it by the first term, I'm going to get x to the n. And nothing's ever going to cancel that. Okay, nothing's ever going to cancel that. Just like nothing will ever cancel when we went through our example. Okay. But everything from there on out is going to interact in some way. So when I take the first term of my binomial and multiply it by the second term, okay, and I'll call this 1 dash 2. Okay, meaning I'm multiplying the first term of my binomial by the second term in my expression to the right. And what is that going to cancel with? Well, this is going to be, think about it, x times ax to the n minus 2. That's going to be ax to the n, not minus 2 because I'm multiplying by x, so it'll be x to the n minus 1. So it's going to cancel with something that is negative ax to the n minus 1. And that will come from taking the second term in my binomial and multiplying it by the first. So I'm going to say this is 2 comma 1, right? The second term in my binomial multiplied by the first term, and those are going to cancel each other, right? And this is going to continue happening. When I multiply the first term in my binomial by the third term, that's going to cancel with the second term in my binomial times the second term. Okay? All right. And so you're starting to notice this pattern. And if you take this all the way to the end, think about what happens when you take x and you multiply it by the last term. Okay? So this would be the first term in my binomial minus the nth term. Okay? And what is that going to be? What is that going to cancel with? The nth term, right? What is that going to cancel with? Well, it's going to cancel with when I take the second term of my binomial and multiply it by the n minus 1th term, or 2 comma n minus 1. Okay, right? You can actually take a look at this for a second. X times a to the n minus 1 is going to be a to the n minus 1, x. And negative a times a to the n minus 2x is going to be negative a to the n minus 1, just like what I had here, times x. And so those are going to be opposites, and those are going to cancel. Okay? And at this point, are we done with all the multiplication? Not quite, right? You'll have to still take this last term and multiply it by the last term here. And is anything going to cancel with that? Absolutely not. I'm done with, that's the only thing I have left. And so this is going to give me negative, because it's a negative a, to the n. And think about the only other thing that didn't cancel. That was this first term times the first term, which was x to the n. And so all I'm left with is x to the n minus a to the n. Okay? So notice here that what was important was that, this is what you want to write down, is that when I have something complex, if I first solve it for a specific case, I can use the same method, and it's important to actually understand what the method was, to then solve the bigger case, right? I noticed which ones canceled and which ones didn't, and then I took that and applied it to the general case. Okay? All right, this should look familiar. This is the statement, the conjecture that we came up with in class after doing the project on the right triangles. And so if we pick any two integers, call them m and n, and we realized what we found is that m must be greater than n, which has to be greater than 0, then m squared plus n squared, m squared minus n squared, and 2mn will be the side lengths of a right triangle. And what we want to do is I want you to go ahead and prove that this is the case. So pause the video right now, write down this conjecture again, and I want you to create a plan for how it is that you would prove that this is the case. And then go ahead and try it. Go for it. Do the best you can, and then we'll talk briefly about it. All right, I hope that went well. So in thinking about a right triangle, and I had many of you just think about a triangle where you have a side of 3, a side of 4, and a side of 5. And if you were very confused, go ahead and think about that for a second. Draw that out and think about how you would prove it. But for any triangle, to prove that it's a right triangle, I can use the Pythagorean theorem, right? So if I can prove, and let me just name these. So let's say this was side C, this was side A, and this was side B. To prove that a triangle is a right triangle, I need to show that a squared plus b squared equals c squared. And if that is true, then it is a right triangle. Okay? And so here in this case, the length of side C is m squared plus n squared. Okay? So what I need to prove is a little more complicated. It's simply that m squared plus n squared, and I'll use here, squared is equivalent to a squared, which is m squared minus n squared. I should have written that in red. Let me go ahead and do that. M squared minus n squared, that's side A, all squared, plus 2mn, side B, also squared. Okay? So if this is true, and I'll put a little question mark here, if this is true, then we have a right triangle. So what we need to do is we need to show that this is the case, right? Our conjecture basically says if m and n are integers where m greater than n greater than 0, then these side lengths make up a right triangle. And so, all right, so what we really are saying is that a squared plus b squared would equal c squared. So if we can show this, then we're good. And I want you to then think carefully about how you would show that. How would you show that this is equal to this? What are we going to need to do? Well, it boils down to us saying, can we make the left side equivalent to the right side? Okay, so the first part of my proof is going to actually be taking the left side and simplifying it. Okay, so that would be the first part. And then the second part of my proof is going to be to take the right side and simplify the right side. Okay, and once I'm done with that, hopefully the left side and the right side, once they're simplified, are the same thing. And so I can come back in my conclusion, the third part of my proof, and say, hey, the left side is equal to the right side. Okay, so if you actually go through and simplify, you are going to get that. Okay, that's going to happen. All right, and I'll show you what the right side ends up becoming. The right side is going to end up being m to the fourth plus 2m squared n squared plus n to the fourth. Okay, and so you can then that should be helpful for you. You can work that out. And then on the left side here, if you work both of these out, you'll find that you get the exact same thing. So pause the video now, go through and actually prove it. Make sure you have it in your notebook, and then go ahead and move on. Okay, so now we're on to the binomial theorem, and I want to spend just a second talking about what the heck binomial even means. So bi, of course, means two, and nomial means number. And so if you think about what that would look like, it would be two numbers. And so in a situation where we are adding or subtracting two numbers, that will be a binomial. And so here is a binomial raised to the nth power, and we'd like to know what exactly happens in this situation, right? If I have a binomial raised to some power, what will it expand to? And this happens all the time. It's used, in fact, to prove one of the most important facts about calculus, which is the derivative of something raised to a power, and it's used in probability theory and statistics quite often. So having some background with this will be very, very helpful as you move on to calculus and further math courses. So we want to kind of just get started, and what we've seen in the past is that sometimes it's kind of hard to jump in and think about the general case. So when I have a plus b to the n, we'd kind of like to pare it back a little bit. So to start us off, let's just think about some really simple situations. Let's think about a plus b to the 0, a plus b to the 1, a plus b squared, a plus b to the third. And so what I want you to do now is go ahead and pause the video and on your own just simplify each of these, and what we're going to look for is a method or a pattern that we might be able to apply into any case, to the general case. And so that's what we're going to be looking for. So pause the video now and go through that, and then we'll talk about how it works out. Alright, so hopefully that went well. Let's think first about a plus b to the 0. Well, anything to the 0 that's pretty simple, right? Anything to the 0 is just going to be 1. And so it doesn't matter what a or b are, it's just going to be 1. And then a plus b to the first power is also pretty simple. It's just going to be whatever that is, or a plus b. And I'm going to write the coefficients of a and b here, and you'll see why I do that in a second. So this is really like having 1a, and this is like having 1b, right? So 1a plus 1b. Okay, now what happens if we square it out? A plus b squared. Well, we can FOIL that out, and that's pretty simple. You end up with a squared plus 2ab plus b squared. I'll write this. I want to center it for a reason. Alright, and I'm going to include the coefficients for a squared and b squared, right? That's just 1 and 1. And you might see why in a second. So now let's think about a plus b cubed. Well, what is a plus b cubed? A plus b cubed is a plus b times a plus b times a plus b. But a plus b times a plus b is a plus b squared. Okay, squared. And we just went through and simplified that, right? We just went through and simplified that. And so what we can do now is we can just take a plus b and multiply it by a plus b squared when we've already squared it all out. So we take a and we'll multiply it by 1a squared. Okay, and we'll take a and then we'll multiply it by 2ab, and we'll take a and we'll multiply it by b squared, and then do the same for b. So pause the video, do that right now if you haven't already. Good. And so what you'll end up with is you're going to have a cubed plus 3a squared b plus 3ab squared plus b cubed. Okay, and once again I'm going to write out the coefficients for a cubed and b cubed. Okay, and at this point I want you to go ahead and pause the video. I want you to look at the cases that we've done here, and I want you to try and write down the pattern that you're noticing. Okay, don't worry about whether it's dead on correct or not. Just take your time and just think about, just look at the different ways that we progress when n is going from 0 to 1 to 2 to 3, and think about how this process is changing. Okay, and what pattern is it following? Write down that pattern, and then we'll go ahead and talk about it. Alright, so let's take a look first at the relationship between the powers of the number. So notice that when the power of the binomial is 0, that the power of a and b are also 0, right? There's no a, there's no b, because to the 0th power it's just 1. Now notice that when the degree is 1, I have degree a to the 1 here, so a to the 1, and then there's no a here, it's another way of saying a to the 0. And here we have b to the 0, and then b to the 1. Okay, moving on, when the degree is 2, we start with a squared, a to the 2, and then we have a to the 1, and then we have a to the 0. Similarly, we started with b to the 0, then we have b to the 1, and then we have b squared. Okay, and then notice with the cubic polynomial, with the cubic binomial, we have a cubed, a squared, a to the first, and then a to the 0. And for b, we start with b to the 0, b to the 1, b squared, and then b to the third. So you should be seeing this pattern, right? I start out with the first term in my binomial raised to the power that my whole binomial is raised to, and with the second term in my binomial raised to the 0th power. And then I just increase one and decrease the other as I move through the terms. Okay? And then what about the coefficients? Well, notice this. This might be a little harder to see, but notice that, let's take a look at this term here. So notice that the 2 is 1 plus 1. Okay? And notice that the 3 here is 2 plus 1. Similarly, the 3 here is 2 plus 1. And notice that the 1s just kind of keep moving towards the outside. Okay? If you wanted to guess, right, what would the next set or the next cascade down b? Well, the 1s would continue down the outside. Okay, 1s would continue down the outside. And then what would happen? Well, in the center here, I should use the black color. Okay, in the center here we have 3 plus 3, which is 6. Okay, then I have 3 plus 1, which is 4. And then I have 3 plus 1 again, which is also 4. Okay, and so if I were to have the a plus b to the 4th power, we could actually write it down, right? We would have a to the 4th, b to the 0. What's b to the 0? 0. It's just 1, so it's not there. Then we have a to the 3rd and b to the 1st, right? Then a to the 2nd, b is moving up and a is doing down, so then b squared. And then we have a to the 1st and b to the 3rd, and then finally a to the 0, which is 1, and b to the 4th. And that would be a plus b to the 4th. And we could just continue moving along this way, right? Where each new row, each new binomial follows this same pattern, okay? And what I want you to do right now is try and write out on your own the binomial theorem. To the best of your abilities, in the general case, what will this look like, okay? And just do the best you absolutely can, and we'll come into class tomorrow and we will talk more about it.